In this video, we're going to implement the increment and decrement circuitry required for registers. Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey. So increment and decrement for this register. Because my memory is going to be laid out such that every read and every write from memory, every read from memory, every write to memory is going to be 16 bits wide. Effectively, what that allows me to do is have my address register increment and decrement by 1, and I'm moving it by the entire bus width, 16 bits. 16-bit computer, 16-bit registers, 16-bit bus width. So ultimately what I'd like to do is figure out how to increment and decrement the values on this 16-bit register by 1. There's nothing that is built into these registers that allow that. They simply store the data. But there is a 74LS183, which is a binary up and down counter. So it provides both increment and decrement functionality. It also has a couple of asynchronous functions, specifically a reset that happens independent of the clock cycle, and a load, parallel load, that happens completely independent of the clock cycle. And that is a favorable thing for us to be able to take advantage of, I believe. There's also a 74LS, and I'm going to grab my cheat sheet here. 74LS169 synchronous binary up-down counter. This one is up here above the highlights. But the challenge with that one is everything is done synchronously, and I don't believe that I want, and it does not have a clear function, so I don't believe that's going to work well for our needs. Of course, I could work around it, but on my cheat sheet, anything that's highlighted in yellow are things that I maintain inventory on. So I have the 193s actually in my case. So this is a 4-bit up-down counter. I need, I'm working with 16 bits, so I'm going to need 4 of these on the breadboard. 4 times 4 is 16. Everybody knew that already. So how would I integrate those into the inputs here, or somehow manage to have this increment and decrement? And the goal here would be to somehow set these 4 up so that the output of the 4 registers, I'm going to have to roll the pins on these, the output of these 4, they're not registers, they are counters, actually fed the register here, and I end up having a dual master situation where both of them maintain the value. Well, I'm not a big fan of dual masters. In my ERP programming day job, anytime you have 2 databases responsible for maintaining the master copy of something, one of them is guaranteed to be wrong. So to solve that, the key then becomes making this the master. It holds the value, and this then becomes the slave. Whatever happens to be in here gets clocked into this register, and then therefore can be distributed out around the rest of the system. So that's I think what I'm going to do. That then leaves this here section on the right side of the board that I can use for control logic. And full disclosure here, I have been thinking a little bit about how to control this, and I'm not certain I've got everything worked out in my head yet, but we definitely have to talk about how we want to control the register and most other parts of the computer as well, and make some design decisions. And so that will be the next video that we take on, is some of the design decisions surrounding the control logic. I don't like the pinning of these. It's really messed up all over the place here. And so I will end up trying to pull wires over the integrated circuits. Ideally, if I had the room, and I don't believe I do, I would arrange it like I did here, where I pulled the wires out to a common spot, which then I could then just tie the ribbon cable lines in directly. And I don't believe I'm going to have that kind of room on this board. So let me get this wired up. Let me pull up the pinning here. I'll put it up on the screen as well. So I have on pin 1, parallel load 1, but pin 15, which is up here next to power, is parallel load 0. And then over here I've got parallel load 2 and 3. So those are the bits that show up for parallel load. Outputs are even more messed up. Pin 3 is output 0. Pin 2 is output 1. So they go in that direction. But then down here, pin 6 and pin 7 are 2 and 3 respectively. So it's 0, 1, 2, 3, which then all need to come up to the inputs into the register up here. And then my loading happens up here. It's not an ideal situation. I did look through some of the other integrated circuits and the pinning associated with those to see if anything got any better. The only one that did was the 169 that I saw. And again, that one doesn't have, I believe, all the functionality that we need. So, the other thing I could do is turn these around so that all 4 of them were at least arranged so that the outputs were close to the inputs. And all I had to do was go straight across the power rails here. I'm not a fan of that. I say as I consider it. And the problem being is that I would absolutely wire these up wrong, and I'd end up cooking a couple of circuits or integrated ICs. But I don't know. Maybe it's worthwhile to do that to keep this somewhat clean. I think I'll do that. And we'll see how that works out. I may regret this decision. Well, I'll get them settled in the breadboard. Let me get power and ground established for all 4 of these. And then what I'll do is I'll take and we'll wire one up as I narrate my way through it. And then once I'm done narrating through that, then I'll go ahead and wire up the other 3. Let me get these settled first. Okay, power and ground are done. I went ahead and took care of the decoupling capacitors at the same time. So, now I want to start wiring up this least significant nibble here. And let's start with pin 1. Pin 1 is my input, parallel input. I'm going to tie that low for the moment. Next in line is output 1. That output 1 goes to the least significant bit of the 74LS574. That's there. Then I've got on pin 3, whoops, I said pin 1, and it should be 0. So pin 3 then crosses over and becomes pin 0. Pin 4 is a control line, and it's the count down, clock pulse to count down. For the moment, I'm going to mark that, tie that low. And then pin 5 is the count up. I'm going to tie that low as well for the moment. I'll come back to those here shortly. Then I've got output 2 and output 3. So pin 6 becomes output 2. And pin 7 is output 3. Continuing on the other side, I've got program 3 in pin 9. So this is my high order bit, pin 3. Pin 2 is next to it. I've got my parallel load control line on pin 11, so I'm going to tie that. That's an active low, so I'm going to tie that high. Then I've got my outputs. My count up and count down outputs. So pin 12 is count up. And that is actually going to go into the next nibble up in significance to pin 5. 1, 2, 3, 4, 5. So that when it's time to ripple or carry or increment the next IC in line, it will provide that signal. And then the countdown, which is pin 13 here, is going to go to pin 4. Finally, I've got master reset. Master reset is tied low for now. And the reason it's tied low is that it's an active high signal. Okay. And then I've got parallel load bit 0 is up here in pin 15. And that is a wire up nightmare. So, everything but these 2 white wires here on the first integrated circuit get replicated up, except for these 2 white wires have nothing else to go to on the end. So it basically ripples its way up from the least significant bit to the most significant bit. Let me get that all wired up then. When I said wiring up these integrated circuits upside down was going to be difficult and I was going to make a mistake, I really wasn't kidding myself. I think I had 2 or 3 false starts trying to get this all wired up. Ultimately, I ended up moving the integrated circuits over to the right, which ended up creating additional issues trying to get things wired up. But ultimately, it ended up following the pattern that I laid out, and everything did end up getting wired up in the end. If you have any questions about the build, please leave them in the comments below. I'd be more than happy to get back to you on those. Okay, now that that's done, a couple of things about the wire up. First, I decided to go from most significant to least significant as I did the wire up. What I ended up doing is I ended up extending the inputs over here to take up, and it's difficult to see on this end, but 0, 1, 3, and then 2. Yeah, the last 2 bits are the most significant bits are out of order there. And the least significant bit is on the left-hand side rather than the right-hand side. But what it allows me to do then is to create a 4-pin ribbon cable, which would be similar to this, similar to the way I broke these up. And maybe it would be an 8-pin that was divided into 2 like this. That would allow me to tie in here as long as I flipped the 2 most significant bits here, then it would work. It would basically be a custom built cable specifically for the inputs here for testing. I can do that and tie them into this board right next to these so that I could use either for testing if I wanted to. So I will work on getting that done. So then I have the most significant nibble here and these 4 bits up here. And then I created 2 empty spaces here for bit 0, bit 1, and then bit 3, bit 2. And then 0, 1, 3, 2, 0, 1, 3, 2. Sorry, 0, 1, 3, 2. So that's pretty densely packed in here. Additionally, I've got the master reset all tied together. That is on here on pin 14. And I've got all the parallel loads tied together so that they're all operates together. And then I've got my count up and count down clocks, which are tied low at the moment. And again, it's the low to high transition that will control that. And the output of the carry and borrow, I believe I have those right. Pin 13 is borrow, pin 12 is carry. So 12 is carry, 13 is borrow, are tied into the count up, count down of the next more significant nibble, so that each one of these ripples up the IC chain. Now, what's interesting about that, if we look at the specification, what you'll see is that the terminal count up, and I'm reading in the right-hand column here, the terminal count up and the terminal count down outputs are normally high when a circuit has reached the maximum count state of 15 for the LS183. The next high to low transition of the count up clock will cause the terminal count up to go low, and will stay low until the clock pulse up goes high again. Coming back to the overhead, normally these 2 pins are high, meaning that the inputs here on count up and count down are normally high, and then they go low right before they're supposed to go back up. So what I'm going to do is I'm going to move these 2 control lines to the high so that it mimics on the least significant nibble exactly what's going to be seen on the other nibbles. And then that's how I will work on constructing the control logic, is to mimic that same pattern all the way across. I also added a decoupling capacitor here for the power rail that I added. And again, this space over here is reserved for control logic, if it'll fit. If I need to, I'll add an additional board down here at the bottom. Okay, next order of business is to make a custom set of cables that will go from my test harness switches up into the register. And once again, these are going to be 4 pins wide for each of those. So what I do have is I have some of this rainbow colored ribbon cable that I'm going to strip down into 4 and create 4 little 4 ribbon cables 4 pins wide, so that I can then turn around and swap 2 pins on those so they're in the right order and get those connected. So you've seen me make ribbon cables before. I won't bore you with that. I will probably just either fast forward or jump all the way to the end when I'm doing the final wire up of those swapped bits. Okay. I now have 4 that are prepped, and I've got one side wired up on each one. And so the next thing to decide is which one is going to be my low order bit. Typically on things like this, the red stripe is the low order bit. But I've got a red that's right in the middle of all of this. And so I just need to figure out if I'm going to have brown be low order or yellow be low order. And it's just a matter of making sure that I get that all set correctly. So I think I'm going to have brown be the low order bit. So when I wire these up, it's going to be brown and then red, and then I have to swap the last 2 bits so that I have yellow and orange in the reverse order. And I hope you can see that crossover right there, right here in between. Let me see if I can zoom in for you for that. So I've got brown and then red, and then crossed over on top of orange is yellow, and then I've got orange sitting on the outside. So that then should be able to compensate for how I have those 193 counters wired on the end, and allow me to create just a real simple connection there. Now this is going to fight me to go in. There we go. Almost. Okay. So bringing the build back to the top. If I plug these in up here, you can see I've got 0, 1, 2 is over here, and 3 is over here on this third bit. So I've got program 0, program 1, program 3 next in line, program 2. And then this end can plug into the board here. Let's slide this down 1, 2. Plug it into the board here, and I will be able to get that programmed very easily. Let me get the rest of these wired up. Now to figure out how to test this. Okay. So the way I have this wired up, I have power coming off this rail here down into this rail for the clock, coming back off of that into this rail on the bottom, coming back off of that onto this rail for the inputs. That'll provide power to everything, but I know I need to get power over here on this side. But in the meantime, I do want to test this. Okay, and I've got my output wired up to the inputs into the registers, which is the outputs from here, and I'm seeing a power problem. And this power problem indicates that I have less than 4.63 volts on this power rail down here. So let's see if I can get that corrected. I'm going to reach for some tools here. So let's start with power and ground over here. And I have a feeling I'm going to be chasing this throughout this entire build. Chasing this being the power problems. Because my power supervisor is so very sensitive, it drops. It throws an error before it gets to very low at 4.3 volts, and then stays off until it comes back up to 4.83. Sorry, let me restate that because I think I stated it wrong. It comes on at 4.63 volts and stays on until the power returns back up to 4.83 volts. And then whatever additional time from this capacitor, and I can see that it's gone out now as I get this ground hooked up. So what I have now is I have power coming all the way down to this rail. So power is coming from here into this, and then from here into this. And so for whatever reason, that additional power path returned this back to high. So off camera, or at least at some point, I'm probably going to add power rails down this outside as well, or power hookups down the outside as well, to make sure that I have power distributed well. Now the input into here, which is the output from these counters, I do want to reset, and my reset is, I gotta pull up my master reset is on pin 14. So if this comes high, it should reset everything. And so it's reset the output off of these counters. And then if I clock that, I should see those return to zeros, which it has. Now, count up and count down. If I want to count up, I move this line up one, and that did not do anything like what I wanted it to do. And then back down. That's a lot of bouncing in there, but I don't know that I've ever gotten it right. Let's try the count. So I'm going to assume that that is working properly at this point, and I know what that means. I'm going to try to set a couple of bits off here, and then do the parallel load, which is bring this low, which should immediately load those in. Let's see here. 1101, 101. That's not right. So I have that flipped, which is a true statement. Each one of these are wired backwards. They should be flipped over. And remember that pin 0, or bit 0, is sitting on the outside here. Get that out of my way. Okay. Let's try that parallel load again. Alright, now let's test or look at what my input is. 1101. That changed at some point there. Maybe because I grounded or shorted something briefly. 1101, 1101, 1001, 1001. 0 1 0 0 0 1 0 0 1 0 1 0 1 0 1 0. Now if I clock that 1 1 0 1 1 0 0 1 0 1 0 0 1 0 1 0. Perfect. Now, if I was to wire, say, for example, the clock up into the clock, no, that's incorrect. I should be counting, and I am not. Oh, clock, tick, 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 yes. I'm getting a couple of bounces. But overall, that's going the right direction. Now let's see here. Let's pulse that. And what I'm seeing is most significant byte is correct. Right. And this is one clock in advance of this. Is that deterministic, and is that what I want? So if I was to reset again and clock, I have 1 and 0. Little bouncing in there. I've got to figure that out. I'm going to drop an inverter in here just for a moment. Let me grab some wires. Not sure where they all ended up. Temporary hookup power and ground. I'll take this to an inverter. No, that should be the output of the inverter. And this should be the input into the inverter. Such that when I clear it, so when I press down, I'm latching. When I release, I'm incrementing. Press down to latch, release to increment. Down to latch, release to increment. So the high clock to latch and the low clock to increment. Now the problem is the parallel load. Maybe that will work. And this is why I've been fighting myself with the control logic. And so for the next video, we are going to get into that. We're going to set exactly how we want things to work. In the meantime, I need to think about this a little bit off camera again still, because it's still not quite straight in my head, obviously. But for the moment, I'm going to call this good. Off camera, I am going to wire the power down the other side of the board so that that is well distributed. And I will remove this inverter here because we have some design decisions to make as well related to the control logic. In the next video, we're going to implement the register control circuitry. There's a lot to consider with this, making sure that we define exactly what we want to have happen on each portion of the clock cycle. I also want to get into troubleshooting that single step bounce that we observed, and I have a working theory right now that it's related to a race condition. Finally is the KeyCAD register circuit design, getting ready for a printed PCB once we get this working the way we want it to. Finally, we do still have our clock related things to take care of, and at some point we'll circle back to these as well.